minutes, but let me start again introducing Sid, who's giving us this wonderful introduction yesterday, all kinds of really useful tools. So please don't walk out of this school and ever forget about generating functions and method of characteristics. You need to dream about these things if you're working in a school.
Uwe, did you mention the 5 p.m.?
Yes, I did. Well, you can. Again, 5 p.m. Don't miss the buses.
The bus is in front of seawall?
In front of seawall, stool, and some people in the past have taken the bus up and hiked back down. So you can try to follow that.
I'll also be organizing a hike back down from the mountain.
Yeah, I can do that. Well, Sid has all these beautiful lecture notes that you can read up on, and I trust you've done that, so you'll have a chance to ask about yesterday's lecture when you start. But also, the grapevine tells you that Sid is writing a book on all this. The co-authors, I believe, are India and London. So, just give it a little more time, and you have a nice volume to put on your shelf and read a lot more fancy tricks and details and fun models on equilibrium statistical physics. With that, let me turn this over.
Well, thank you very much. Okay, so this is my second lecture, and in fact, let me begin this lecture with how I should have introduced the first lecture, which is that I'm presenting 4 disparate topics in non-equilibrium statistical physics. And these 4 topics are actually 4 chapters out of a book that I'm writing with Elie Venay and Paul Kuczynski. So they're actually little pieces of 4 chapters. And I hope this book is going to appear in a time scale of 1 year from now. And hopefully the completion of the manuscript in a couple of months from now. Unless I go for a hike and then I lose 1 day of corrections or something like that. Okay, so today, yesterday's topic was aggregation kinetics. And I also want to make clear that on the topics I'm presenting, aggregation kinetics, it was mainly classic results that were already known like for 30 or 40 years, perhaps recast in a somewhat more modern context and using some tools that I've learned along the way. So none of that was my work. I just want to be sure that you appreciate that. In the topic I'm presenting today, which is absorption kinetics, I've never worked in this field. So in principle, I know nothing. But nevertheless, I find it to be a very beautiful story and a very nice application of tools of non-equilibrium statistical physics. The next lecture on Thursday is on first passage processes, and in principle, I've not really worked in this field per se, but I've written a book on the subject, so I guess I know something about it. So I'll just present some basic facts about it. And then the last lecture I'm giving on the growth of complex networks, I have to admit I have worked on it, and so in fact I even have like a keynote presentation, so that'll be for Friday. Anyway, so let's start with absorption kinetics. Stellar. So what is the problem? The problem is that I have some kind of a surface, so something like this, and there are gas molecules which are diffusing around, and they impinge on the surface, and they might stick to the surface. And so you have another gas molecule, and it comes and it sticks, and eventually the surface will get filled up with these absorbed molecules. And one can imagine that there's a perfect absorption, which is that a particle sticks, and it sticks forever and never moves, or there could be some desorption, or the particles could actually diffuse along the surface. And I'll mostly focus on the case where it's perfect absorption, that a particle hits and it absorbs forever and it doesn't move once it's on the surface. And so the question is, what happens? And so let's look, first of all, at the simplest possible case we can imagine, which is monomers in 1D. So what I imagine now is that my surface is a little one-dimensional line, and these little cups are meant to denote the absorption sites. And if monomers are floating above in a gas phase and they absorb onto the sites, then eventually it's clear that the surface will gradually fill up. And so for monomers in 1D, we can write rho, which is the density, and we can write a rate equation for how the density changes with time. And basically, rho dot, the time derivative of the density, will increases at a rate which is proportional to the density of vacancies. So I'll write this as 1 minus rho. In principle, there should be some reaction rate or some absorption rate in front, but let me just rescale it away to d1. And then for this problem, it's simple to get that rho of t is equal to 1 minus e to the minus t. So that's like sort of kindergarten absorption parameter. The next level of problem was first introduced, I think, by Flory, either in the 30s or the 40s, and it's a really beautiful problem, and it's dimers in 1D. So again, here is my one-dimensional lattice. I'll draw the cups a little closer together. And now the things which are absorbing are dimer molecules. So here is a dimer floating around in the gas phase. And the way it absorbs is that it has to come and occupy 2 surface sites. And maybe another dimer comes along over here, and it absorbs onto these 2 surface sites. And already you see at this level there's something interesting going on, because now there's a site in the middle, a single isolated site, that can never no absorption can take place on it. And so in the case of dimer absorption in 1D, instead of ending up with the final density going to 1, the final density here, rho infinity, or rho t going to infinity, is clearly less than 1. And so the basic question to ask is, what is this final density? So it turns out that this final density, in fact, I know what the number is, it's equal to 1 minus e to the minus 2, which is something like 0.864 ... And so this number was first calculated by Flory in a very beautiful paper. And if you want to be a little bit intimidated, read his paper, because he is really a master at combinatorics, even though he was trained as a chemist. And so he figured out a way to enumerate all the possible dimer states and all the different configurations of vacancies and actually calculate this number. And it's depending on your mood that day, you can either be completely inspired, wow, this is wonderful, this is great, or you can be really bummed out, I'll never be able to do this. So okay.
Quick question.
Yes.
So it seems like in this model we've assumed that you can't have perpendicular absorption.
Correct.
And is there a reason that we did that, or can we consider that problem?
Oh, absolutely. I mean, this is like the simplest scenario. Okay. I mean, you know, once you start playing the game, there's all kinds of things you'll start to see that you can start doing with playing with. I mean, for one thing, one-dimensional substrates, typically this is going to be more relevant for polymer-type problems. But once you do this on a 2-dimensional lattice, then there's orientation going on. And roughly speaking, one-dimensional problems are eminently soluble, and 2-dimensional problems are basically unsolved. Okay. So anyways, I want to now calculate this number 0.864, ... And it turns out that some community of people along the way realized that instead of solving the equilibrium statistical physics problem of enumerating all the states of dimers in one dimension, let's look at the problem from a non-equilibrium statistical perspective and study the evolution of the coverage as a function of time. And it turns out that the calculation of the coverage as a function of time is not so difficult to do. And then for free, we're going to get this answer. And in fact, we'll get a lot more because we get the coverage, the time-dependent behavior of the coverage. So the goal is then we want to find the time-dependent coverage. And the thing is that there's 2 basic dynamical variables that help us to characterize the state of the surface as a function of time. And in terms of these things, we can write down master equations for their evolution and get the surface coverage. So one basic quantity is, let me call Vm. So this would be equal to the probability of a void of length m. And so schematically, this would be the probability. So let me use capital P for the probability of the following configuration: an occupied site, and then m empty sites, and then an occupied site. So this is exactly equal to m. So the point here is that, you know, as the surface is getting filled up, well, if the site is occupied, then it's dead. And so the only place that action can occur is where there are empty sites. So we should understand the dynamics of empty sites. And in one dimension, the empty sites naturally organize into these voids. And so if we understand the evolution of the void distribution, then we will understand something about the dynamics of the problem. Now, it turns out that this void density is not as useful as you might think, and there's another quantity which is closely related, which we'll call E sub m. And I'll define this to be the probability of an empty interval of length n. And so this empty interval is kind of not very precisely defined here, but let me define it this way. I'll write it as probability, I'll write it as x, and then m empty sites x. And what I mean by x is unspecified. So this I will also write as probability of m empty sites, and I'll just forget about what's on the outside. So the idea of the empty interval probability is that you imagine looking at your line with blinders that have length m, and you just take your blinders along and say, is this m interval all empty sites? And if it is, then it adds 1 to the number of empty intervals. And I don't care what's happening outside. And it turns out that the equations of motion for the empty interval probabilities are different and simpler than the equations for the void probabilities. So depending on the application you want, sometimes you should use the void densities, sometimes you should use the empty interval densities, and it's not obvious a priori which is best. And it turns out in this case, empty intervals will be best. Yes?
Can you recover one from the other?
Yes, I'm going to come to that momentarily.
I'm confused about the denominators. Are we grabbing a site at random and it's probability that it's found in a void? Or are we grabbing a void at random and then the probability that's like that?
Well, so what I'm saying is that, I have my line interval. So let's compute the empty interval probability. So here I'd say I have a line of a certain length. I choose my blinders this big, say length 3, and then I say, okay, here's an empty interval of length 3, then I move over here, that's not an empty interval, that's not empty, and go down the road, and then this one is empty, so I found 2 empty intervals, and the rest were not empty. And for voids, I would say, well, I want to look for something that looks like this, and so I'd have blinders now of length 5, I want to find a void of length 3, and say, is there 2 occupied sites and 1 empty site in between? I just count the number of these, divide by the total number of sites. Okay. All right, so actually, in response to Jordan's question, let's actually spend a little... I'm going to deviate from my written notes. I'm going to talk about a little bit about the relation between these two things, because, once you start getting into solving a problem, I'll only solve the simplest one, and it gets a little bit, again, detail-oriented, so it's better maybe to spend some time just discussing some of these basic issues, which are simple and important. So what is the relationship between this VM and EM? And by the way, one other thing, maybe for a plug that's going to happen next week, I'm sure that Danny Ben Abraham, he's talking about one-dimensional diffusion-limited reactions. And he has a very grandiose title, like some miracle or something like that, about the empty interval probabilities. And in fact, he will use the empty interval probabilities, I'm sure he'll use this stuff to then solve exactly the one-dimensional diffusion-limited coalescence and annihilation processes. So let's relate VM and EM. So the way we're going to relate it is by some sort of trivial probabilistic arguments. First thing is the probability of having an empty site versus the probability of having an occupied site. Well, that's clearly 1. A site has to be either empty or occupied. If I continue this sort of reasoning, I can say P00 dot plus P0 occupied. What is this? So the left side is empty, and then the right side is either empty or occupied. This is nothing more than the probability that a single site is occupied without paying attention to its right neighbor. Let me do one more of these things. If I do P00 plus P0 occupied plus P occupied 0 plus P occupied occupied, well, I've just enumerated all possible states of 2 sites, and so this is equal to 1. So with that preliminary now, let's relate VM and EM. So let's look at the following quantity. P0000, an occupied site. And let's suppose that there's m of these guys, which are empty. Well, if I then compute P, m empty sites, and this guy also empty, well, what is this? This is nothing more than P for empty sites. So, what is this guy though? By the definition over here, this is nothing more than E m plus 1. This is exactly EM. So I get the relation that P, m empty sites, and one occupied site is equal to EM minus EM plus 1. Now let's do the same game on both sides. So let's do P, occupied site, 4 empty, occupied site. And so what I'll do now is just enumerate the states of these 4 boundary sites. So I can write this plus P, occupied, 4 empties, and empty say, plus P, empty in the first, 4 occupied in the row, this guy occupied, plus P, the first site empty, the next 4 sites empty, the next site empty. So I've enumerated all possible states of these 2 boundary sites, and so that's nothing more than P, leaving the boundary sites out of the problem altogether, and this 4 empty sites in the middle occupied. So this guy is exactly what we're calling VM. And this guy is, what's this guy? Well, let's see. So here we have m plus 1 empty sites. And so according to this little cartoon, this thing with n empty sites is this guy. So this one is equal to E m plus 1 minus E m plus 2. This guy's the same thing back again. So it's plus E m plus 1 minus E m plus 2. This guy is plus E m plus 2. And this is equal to EM. So finally, we get a very simple relation, which some of you who are good at probability theory might have figured this out without doing any of this stuff. We have VM is EM, EM plus 1 minus 2EM plus 1, and EM plus 2, we have 1 minus 1 minus 1, so we have plus EM plus 2.
There's no 2.
No 2, thank you. So, another way of putting this is that v of x in the continuum limit is nothing more than the second e by the x squared. So, there's a simple relation between those 2 things. So if we know v, we know e, and vice versa, and so you should choose whichever sort of elementary excitation is simplest for solving the problem at hand. And I'm looking for the brushes. I just found it. Okay. So let's now solve the one-dimensional dimer adsorption problem. And in this case, let me write down the master equations, both for the empty interval probabilities and for the void probabilities. And you'll also see from this formulation that the empty interval probabilities are perhaps a little bit simpler. So I want to write down an equation of motion for E m dot. How does this change with time? And so there are 2 ways that an empty interval can change. So again, you think about, you're looking at your one-dimensional line of these blinders, and how can this empty interval change? There's 2 ways it can happen. You can either deposit dimers somewhere in the interior of the interval, and so there's going to be a term here which is equal to minus m minus 1 En. And pictorially, if I have an interval of length m, so we have 4 sites here, then I can put the dimer on the first 2 sites, 2 and 3, 3 and 4. There's 3 ways to stick a dimer into an interval of length 4, and in general, m minus 1 in an interval of length m. But then there's 2 other ways that you can kill a interval of length m for the following thing. You can put one in an interval of length m plus 1. So for example, if this site happened to be empty, which happens to probability em plus 1, I could put a dimer here, and then one side of it would impinge into the interval, and then would contribute to a loss of this m interval, and it can happen on either side. So that is the equation of motion for the empty interval probabilities. One thing to note about this equation is that every term is the same sign, and that same sign turns out to be a helpful thing in trying to solve the equation. Let me just, for the sake of completeness, let's write down the equation for the void densities. So if I wanted to solve for the void densities, then there's 2 terms. there's a minus m minus 1 em. Just as before, if I have now a true void, which means that these two outside sites are occupied, then again there's three ways of sticking a dimer in this void at length 4. So that's the only way I can lose. I can't put a dimer that's just impinging on one because it can't absorb here. So in fact, there's another term in this equation which is actually a gain term. And the gain term comes because it can take a much larger void and deposit a dimer in the right place such that one of the two constituent subintervals is created as of length m. And so there's a summation here, 2, summation m plus 2 to infinity vm. So this is a fragmentation term that describes you take a larger void of length n and you cut it by putting a dimer somewhere in the middle, and one of the two voids is of length m. And there's two ways of taking a much larger interval. And I can put my dimer, say, here and create m over on this side, or I can put it over here and create m on that side. So that's why there's factor 2. So I leave it as an exercise for the students to solve the problem using these void densities. But I'm going to just work with the empty interval probabilities because the sign is the same. So you see here, because the signs are different, these two terms are competing. And typically in differential equation problems, when you have two competing terms, they might cancel each other out, or they might be different orders of magnitude, and you don't know is the sign of this positive or negative. Here it's obvious the sign is negative, and it's much easier to deal with. All right, so let's now solve this equation. And the thing is that let me write it in a way that's suggestive. So em dot plus m minus 1 em is equal to minus 2 em plus 1. And so, from freshman or sophomore differential equations, it kind of looks like a framework to write an integrating factor. And so, in fact, let me now make the following ansatz, which is e to the minus m minus 1 t, and let's call this other function left over phi of t. And again, from sophomore differential equations, this is precisely the integrating factor for this equation. It turns this into a total time derivative. So let's try this function and substitute it into the first equation and see what comes out.
So can I ask you?
Yeah, question?
Yeah, in the first equation that we got, I missed something. So you laying down dimers?
Dimers, yeah.
Yeah, so why is it EM cannot disappear by laying out a dimer in the middle of...
No, but you can. So that's what this term is describing for, that you're depositing a dimer somewhere in the interior of an m interval. And there's m minus 1 places it can be deposited.
Can you repeat the second term how you have the gain?
This one, yeah. The meaning of it? Yeah, so the meaning is that I have an n interval, and I put down a dimer, say here, for example, and I create an m interval, and then this is going to be left as an n minus m minus 2 interval, and this was obviously 2. And so I can put the dimer over on this side, or I can put it on that side, creating an m interval from the fragmentation of an n interval into now one of size m and one of size n minus 2. Okay. So let's just plug this in. And so what we're going to get, well, when I differentiate this guy, there are two terms. One where I differentiate this, and I get precisely that term and cancel out. And another one where I differentiate that guy. So on the left-hand side, I'm going to have e to the minus m minus 1 t, phi dot. And the term where I differentiate that is going to cancel by this guy. And then I have minus. And so that's equal to minus 2 em plus 1. So that's equal to e to the minus m t. This is em plus 1 on phi t. Or phi dot is equal to minus 2 e to the minus t phi. Or the solution is phi of t is equal to, and so the one thing about these sorts of problems which makes it a little bit funky is that, the solution of this equation is trivial. It's just the exponential of the integral of this thing. So you have exponentials of exponentials. There's always double exponentials floating around. So what one gets here is e to the minus 2, the integral from 0 up to t, e to the minus t dt. And the one thing the coefficient here should be phi at t equals 0. If I start with an initially empty lattice, then all the EMs are 1, and so at t equals 0, the phi is 1 as well, so there's no initial condition. Hope I did that right. And this thing then is equal to e to the minus 2, 1 minus e to the minus t. Okay, so now we're almost done. And you sort of see that there's like an e to the minus 2 here that might be reminiscent of this Flory number. So what we have then is em is equal to e to the minus m minus 1 t minus 2, 1 minus e to the minus t. In particular, e1 is equal to e to the minus 2, 1 minus e to the minus t. And the final step of this is now, where is the density in all of this? Well, E1 is the probability that a single site is empty. So the density is nothing more than 1 minus E1. Is equal to 1 minus e to the minus 2, 1 minus e to the minus 2. And one sees that as t goes to infinity, you get 1 minus e to the minus 2. So I'd like to argue that this derivation is much easier than what is in Flory's original paper, and you can check it out for yourself. And as a byproduct, we get the full time-dependent coverage for any time. So I think that it's a very useful technique for these sorts of problems.
Can you, is there, what's the physical reason for 2?
Well, I mean, the two comes from the 2 over here, which came from the 2 ends, but like, yeah, that's the best I can say.
What about trimers? If you deposit trimers, it becomes 3.
Okay, so, well, in fact, as an exercise for the student, you can do, and in fact, it's done, I guess it's not in my notes, but it's in my book, but it's a straightforward generalization. You can then deposit Kmers on this, and then you'll have like a K, it's basically an m minus k em, and then there's like a 2 here, but it will be em plus k, and you can play it all out, and everything works out. It just gets, the formulas get much more ugly looking, but it's the same, everything's the same. So it's actually a good exercise to check that you follow this.
So just for the fun of it, 2 is the surface area of a one-dimensional circle.
That is a true statement.
Does it go to 2 5 dimensions for something similar to this?
Well, so the point is that...
Can you repeat the statement?
Yeah, what is
Oh, I'm sorry. The statement was that 2 is the radius of a circle in one dimension. Surface of a circle in one dimension. So isn't there some sort of obvious generalization of 2 dimensions? Somehow there'll be a 2 pi or something like that. And so the answer is that in 2 dimensions, all of this goes out the window. There's no exactly soluble model. Well, there's only one exactly soluble model in greater than 1 dimension. That's on the Cayley tree. And the crucial point here is that the elementary excitation, these intervals, are a simple topology. And as you continue to break up the lattice, the topology stays simple. There's only one-dimensional intervals. Once you go into 2 dimensions, then the shape of the empty islands are complex, and you don't know how to enumerate them all. On the beta lattice, they're still simple, and so that's why this beta lattice is soluble by a simple, generalization of this technique. Okay.
But are there some results from like simulations in 2 dimensions?
Oh yes, I mean 2 dimensions. I mean there's been like 20 years of people simulating every possible model you can imagine: oriented dimers, unoriented dimers, Kmers, things that make L shape. There's a beautiful review article by Jim Evans, The Reviews of Modern Physics, maybe 20 years ago on this subject. I can find the right reference, but it's a very active field. Okay. One other thing just to point out about this is that you might ask, well, how quickly is this limit approach? And so let's look at rho infinity minus rho of t. And so that's equal to 1 minus e to the minus 2 minus 1 minus e to the minus 2, 1 minus e to the minus t. And so the 1's cancel, and so I have e to the minus 2, 1 minus e to the minus t, minus e to the minus 2. And so at a long time, I can write this as e to the minus 2 times e to the minus 2, e to the minus t, minus e to the minus 2. And now I extend this in a Taylor series, and I'm going to get e to the minus 2. So the first term is 1, which cancels that guy, and the next term is, so it's 2 e to the minus 2. So this is the rate at which you approach the final state exponentially quickly. So the next level of complication is, let's talk now not about, so the question was trimers and k-mers and all that, but a more interesting problem is, let's let k go to infinity and have cars that are of an infinite length on a substrate. And effectively what I want here is, I'll take the limit as k gets large, but it's still small compared to the size of the lattice, so that the position of where the car or the k-mer can land, it becomes continuous. And so I can now talk about the deposition of unit length cars. I keep coming to cars, because we're going to be thinking about parking, that can absorb on the continuum line. So let's talk now about car parking, which presumably we all have some experience with. So for car parking, the same kind of picture goes for the equation of motion for the empty integral probability. Now the basic quantity is not the empty interval probability of discrete size, but let me call ext the probability of an empty interval of length x at time t. And so let me write down a similar equation of motion. And it turns out one has to be a little bit more careful here, because one has to distinguish between parking in a space which is big enough to accommodate the car, or parking in a space which doesn't accommodate the car. I mean, you can still do it because I'm looking at E, which is the probability of having an integral parking space of length x or larger. So there's a way of squeezing in if your car is too big. So now let me write down the analog of this equation of motion. So ext. So I would say it's equal to 1. It's equal to x minus 1, ex. Now I'm going to be lazy and drop the time index so I don't keep running too much stuff. So that's like the analog of the first term here. If I have a car of length 1 and a parking space of length x, and I can put my front bumper anywhere from 1 to x minus 1, and the back end of the car will be outside the parking space. And then there's the analog of this guy. And what it is in this case is going to be twice the integral from x to x plus 1 dy dy. So pictorially, what is the second term here? Is that I have my integral of length x, but outside is unspecified. So here's my car, which is of length 1. And so it can park if this region here, y, is anywhere between x and x plus 1, then the car will park, and some part of the nose of the car will go into the parking space and decrease the density of intervals of length x. So this is a generalization of the first equation I had over there. The thing is that I've implicitly assumed in running this equation that x is larger than 1. And there's another equation that says when x is less than 1. So when x is less than 1, how does an interval of size less than 1 change? Well, again, because it's empty interval probability, let me write down the first term, and then it'll be, I hope it's clear what happens. So for this guy, if I want to lose an empty interval, so here's my car now, of length 1, and here's my empty interval of length 1. Well, I can kill this empty interval of length 1. I'm sorry, this is empty interval of length x, which is less than 1. This is of length 1. So a car can, like this Hummer, can park in this tiny parking space if outside it's also empty. And, so in order to have that, we must have an E1. And so roughly speaking, in terms of like making a pictorial representation, this first term is essentially the same as that term, except you interchange the role of the car in the space. In the first case, the space is bigger than the car, and we got that. In this case, the car is bigger than the space, and you just interchange the roles of x and y. And similarly for the last term, you just interchange the roles of x and 1. So you get 1 to x plus 1, ey dy. So those are the master equations for this process. And again, one can solve these master equations by the same line of reasoning as we did over here. So let's try the following ansatz. The presence of this term, again, suggests an integrating factor. So let's try ext is equal to e to the minus x minus 1t times some function phi. But this function phi is actually nothing more than e1t. Because you see that if I plug in x equals 1 over here, the exponential goes away, and so what's left over is, by definition, e1t. So now, in fact, we know what it is. We don't have to call it phi. So if I try that and plug it into this equation, let's see what happens. So let's first of all look for x greater than 1. So when I differentiate, there's a term where I differentiate the exponential, and that's just going to be canceled by this term there, so I'll just forget about it. And so I'm going to have e to the minus x minus 1t, e1t. I won't write the time argument because I'm lazy. So that's when I differentiate, slow down again. I want to compute e dot. So the first term is when I differentiate this guy, and that'll be cancelled by this. The second term is I differentiate that guy, so I'll have e to the minus x minus 1t times e dot. And then I have minus 2, and then I've got to write e to the minus, I guess I have to have it inside the integral. So I'm going to have 2 e1, and then the integral from x to x plus 1 ey, which is e to the minus y minus 1t dy. And so allow me not to do the integral. This is equal to. Allow me not to do the integral because this is precisely the kind of thing I always screw up. And so I don't want to screw it up in front of you guys. Let me just tell you what the answer is here. E1 dot is equal to minus 2 over t, 1 minus e to the minus t, d1. So it's very similar in structure to what we had over there. And so the solution then for E1 is E1 is equal to e to the minus 2, the integral from 0 to t, 1 minus e to the minus u over u du. So we're almost done, because what I found here is like the analog of phi, but what we really want are the coverage probabilities, and ultimately we want the coverage of the system itself. So how do we get the coverage of the system itself? And so for this case, let's look at the equation for, this was the equation here for x less than 1, was the second equation. Let's look at E0 dot. So for the second equation, E0 dot, well, I plug in x equals 0. This term goes away, and I just get equals minus E1. So this probability of having an integral of length, empty interval of length 1 is related to the time derivative of E0. But E0, I claim, is rho is nothing more than 1 minus E0. So if I have an empty interval of length 0, that means I have an infinitesimal region which is empty. 1 minus that probability is the probability that that infinitesimal region is occupied. And so that's nothing more than the occupancy of the lattice. So we finally get our answer for the occupancy of this continuum, actually. It's not a lattice, it's a continuum parking lot, by taking the equation for E1, integrating it to get E0. So I have to integrate this one more time, take 1 minus that, and then I'm going to get the density. So again, allow me not to do those straightforward steps, but let me just write down the answer. And so one has a rho of t. So this one called this rho of t is equal to 1 minus E0t. So this thing is equal to integral from 0 up to t. And then I have e to the minus 2 integral from 0 to t, 1 minus e to the minus u over u du. and the whole thing is dv. So the hard part I find in writing these formulas is to keep track of what's in the double exponential, what's only one exponential high, but that's the answer. And the thing about this is that in a limit as t goes to infinity, this converges to a finite number which is less than 1. And that finite number is like something like 0.74747 ... It was first computed by Renyi, I guess, in 1950, so you can call it the Renyi constant. So this is another beautiful absorption problem in which the exact solution exists. Now, there's one last feature about this absorption problem that I want to contrast with the case of the discrete substrate, which is here we found that for the discrete substrate, the probability, or the rate at which you approach the final state, varied as exponentially. So you exponentially quickly became fully occupied. In the case of cars, the approach to the final state is actually power law in time. So let's look at, again, rho infinity minus rho of t. So rho infinity I integrate to infinity. I subtract rho of t, which is integrating to t. So the difference is just the integral from t to infinity of everything here. So this thing is equal to the integral from t to infinity and all this horrible stuff. Let me write it exponential. And then I have minus 2, the integral from 0 to v, 1 minus e to the minus u over u to u, and then the whole thing dv. So what do you do with something like this? Well, if you're really good with special functions, I mean, this can be all related to like exponential integrals, and one can calculate everything. But if you don't know that, let me show you a really cheap and sleazy way of getting something out of this. And I find this trick extremely useful because I use it over and over again when I'm dealing with Laplace transforms. Because, you know, in Laplace transforms, you will have integrals and exponentials of something. And in this particular case, the insight about how to get something useful out of this is if t is large, we're integrating, so if t is large, sorry, did I make a mistake? Yeah, I want to say v is large, but... Yeah, so the point is the lower limits, so v is at least as big as t, so if t is large, this upper limit is large. And so what we're doing is integrating this function, but let's look at what this function is. So here we have 1 minus e to the minus u. So at 0, this function is 0. And then as u gets large, then this goes away and it becomes 1. So this function is crossing over from 0 to 1. Now let me do just something really sleazy. Just do that. And it happens when u is equal to 1, that this will cross over. So I'm going to replace a smooth crossover by a sudden crossover. So if I do that sudden crossover approximation, then what's inside the exponential is the integral. So I forget about this business, and I just have 1 over u du. And I integrate, well, it's integrating from 1 to v. And this is nothing more than 2 log v. So this is minus 2 log v. But this is all inside the exponential. And so this is just minus v squared, which I then integrate. And so I'm going to get from this 1 over 2. So the interesting thing here is that the approach to the final state is power law rather than exponential. So this notion of when you have continuous degrees of freedom, the approach is much slower. Power law character seems to be a feature of the continuous problem.
That's true just in one dimension, or is that strange continuous limit?
I'm coming to, it's like I almost paid you to ask that question because I'm not. No, it's excellent because I'm going to not talk about the same thing in higher dimension. Yes.
Sorry to change the topic, but
Sure.
There's an implied, you had rates that are order unity, rates of which these things get positive.
Right.
And it seems to...
Well, it's all been scaled down here. I'm kind of assuming the rate of 1.
Right, but it's a rate of 1 of successful parkings, right? Like you don't have in your model that it might try to park and fail, and might try to park and fail.
Well, the thing is that you imagine that you have kind of like a gas of particles that are all, or let's talk about the streets. You're cruising the city streets looking for a parking spot. And if you miss the parking spot, someone else grabs it for you, then you've got to go back into the gas of particles looking for parking spots. But but one can actually do other things, which is that if you miss a parking spot, like you hang around for a while, like a diffusion control process, and maybe go to some other near parking spot. But here I'm assuming kind of a mean field picture that once you get rejected, then you're sort of back into the gas of people looking for parking spots and just roaming randomly. Yes?
So, is the continuous noise the same as the Kramer problem? It's still goes to infinity?
Exactly so.
Then you can see a crossover between exponential and modulo?
Exactly so. Exercise for the student. That's a great exercise. Thank you. Okay. So, let me talk now very briefly about higher dimensions, because the available results in higher dimensions are quite meager. In fact, the only well-known, or the only kind of well-established result is what I'm going to show you now. So this is absorption in d greater than 1. And since I can only draw on the blackboard 2 dimensions, the picture will be for 2 dimensions, but I can easily generalize the argument for arbitrary dimensions. So let's look at a simple continuum absorption problem in 2 dimensions. Let's look at the absorption of disks. So here's a disk which absorbs, and here's another disk that absorbs. And it's obvious that as I absorb ad infinitum, that eventually the system will get jammed, and there'll be some final coverage, which is not 1. And one can ask, what is the final coverage, and what is the approach to the final coverage? So the final coverage is very much detail dependent, but the one thing which is universal is the approach to the final coverage, whatever it happens to be. And so to see how this comes about, notice that if I put a disk over here, then so if this is say radius 1, then there's an exclusion zone of radius 2. And if I put a disk somewhere inside this exclusion zone, it can't work because it will overlap. So there's an exclusion zone. So another disk, the center of it has to absorb, say, over here. So here's my disk of radius 1. And the 2 exclusion zones have to be such that the exclusion zone of one guy doesn't overlap with the other particle over here. So now you can deposit these disks anywhere where there's no exclusion zone or no particle itself. So there's as time goes on, there'll be these little tiny target zones where there'll be nothing. So here might be another exclusion zone, here's another exclusion zone, and so here we have a target zone. And so this is the only place it will be able to absorb, is where there's no particle or no exclusion zone. And as time goes on, these target zones will tend to be very tiny. And so when all these target zones have disappeared, that corresponds to when the system is completely jammed, and then you're stuck. And so let's now investigate the behavior of this target zone. So let's suppose I have a target zone which has a characteristic length scale L. And let me call C, L, T the density targets of linear dimension L. So clearly these target zones are going to disappear because you're absorbing at some rate. And so let me write down a rate equation for how this thing decreases with time, CLT.
So does it matter what is the smallest target zone, smaller or larger than the radius of the...
Well, I'm thinking about the long time limits, so when the target zones are very small. Because when they're big, then the notion of a target zone is sort of, it's not terribly helpful. So let's imagine we let the process run for a very long time, so most of the absorption attempts fail. And so clearly all that's going to be left will be small target zones here that have this kind of Apollonian type shape to them.
But what I mean is that there's a smallest target zone.
No, because once the target zones reach 0, then that's when the system jams. There's no, if I have a target zone like this, that means that a particle can absorb here, and once it absorbs, it completely covers it, and then there's no more target zone at all, and that's when the system will jam up.
Suppose I have 4 particles right there, the ones that you drew.
Yeah.
So if they're really close packed, that's in the square arrangement.
Okay.
The target zone, that's the smallest one you can have, right?
No, I think you may be forgetting that you respond to exclusions. The target is not.
No, I'm including exclusion region.
No, but the thing is that, maybe this is an unfortunate way of drawing the picture, but the point is that this target zone can be of any size because, you know, if I bring these really close together, like the particles themselves are barely touching.
Right.
Then the exclusion zones are doing something like this. They're completely overlapping. And so the target zone has actually been targeted out of existence.
Oh, okay.
Yeah. So there's no notion of smallest target zone because it can be size 0. So anyways, I want to calculate a rate equation for how these things disappear. So what I would say is the following. That I have a target zone of linear dimension L, so it has an area which is of the order of L squared. So the probability, or the rate at which a target zone of length L, linear dimension L, disappears will be proportional to the density of such target zones, CL3, times the area itself. So the rate at which you disappear, it's a density, and then times the area, because that's the probability that a particle can land in such a target zone. And so the solution to this will be CLT is proportional to e to the minus L squared t. So the target zones of a particular size are vanishing exponentially in time. But the crucial point is that there's target zones of all possible L's that are available, and that's what's going to end up giving power law decay for the density. So now let's look for the equation for rho infinity minus rho t. How does this evolve with time? And so what I would say is that every time that the point is that every time that you add a particle, the available space is decreased by a constant amount. And so that the deviation of the density from the final density is just proportional to the density of target zones themselves. And what I have to do then is just compute. So what is the density of what is the area covered by the target zones? It's nothing more than CLT, and I have to integrate over all L. And so this gives me e to the minus L squared t dl, integrated for all L from 0, the lower limit is 0, up to infinity. And this integral, just do by scaling, just put a square root of t here. There'll be a 1 over square root of t out in front, and then this whole thing here is just a number of order 1, and one gets that the asymptotic approach is 1 over t to the 1/2. And for general dimension, this would go as 1 over t to the 1 over the dimension of space. That same argument works, yes?
I'm a bit confused with the exclusion. So the exclusion is always double the size of the...
Yes.
Okay.
Yeah, because again, just from pictorially, if I have my particle here, say of radius 1, then there's no way I can put a particle within whose center is within a radius within this exclusion zone, because then it's going to overlap with the particle itself. So there is this exclusion zone, and it's radius twice that of the particle. Yeah.
You evidently don't need to worry about a gain term for your CL and T. Is there an argument why that's irrelevant?
Well, in principle, you see, if at the early stages of the process, this notion of having kind of a compact target zone doesn't make any sense because it can be very convoluted in shape. But if I'm willing to wait to the very long-term limit, then my target zones are tiny, and then there's no way you can gain them because once they're covered, they're going to be completely covered. Or, you might, just by very good luck, it could be that you have a particle that you put over here, and then it partially covers the target zone, and so it got just smidgen smaller, but you can't create target zones.
Would that create the target zone?
Pardon?
Well, you can. I think what Ben is saying is that would have taken a target zone of L plus 1 and made a target zone of L.
Yeah, so, but you see, this, what I wrote here, okay, good point. What I wrote here was the equation for the time derivative, so that's going to be the difference. So that's what precisely this is. So there's a gain term because I made this a little bit smaller, but that's included by the first derivative here. Yeah, Dan.
So is this process similar or the same to the random loose stacking of spheres, of circles that we talked about yesterday?
No, not at all, because once you're filled, like all the particles are basically not at all touching. So in fact, everything's rattling once you reach, once you can't deposit anymore. The particles aren't touching at all. But,
So depositing in higher dimensions means can I fit another guy in there, but you're not talking about how to get there.
That's correct. Yeah, so very good point. Yeah, so it becomes a little bit artificial in higher dimension. At least two dimensions. They could fall down from higher dimension, but then typically they're not going to get to that one available target zone because it's inside of some cage and you can't reach.
What about the other dimension of the target zone? Like, can you write like a density of with two variables, like an L1 and L2?
Well, in principle, I should, but the thing is that, these target zones are arbitrary shaped. I mean, I could have something which looks like a little triangle, or it could be a little rhombus or something like that. So to characterize all these shapes properly, it is not, I'm not doing that properly, because I'm just saying that, roughly speaking, I'm assuming that these target zones are isotropic, and that they're characterized by their linear dimension in an area which scales as the square of the linear dimension. So this is a rough argument. It's certainly not rigorous, but it gives the correct asymptotic behavior. That's all I'm looking for. Yeah.
Would it be by changing to radical-positive ellipses instead of circles?
Okay. For ellipses, it is possible to give an argument, which I don't dare give here because I'm not sure I even believe it, but if you, people have come up with an argument as t to the minus 1/3 approach to the final state. And roughly speaking, the argument is that if you deposit ellipses, that they tend to align in some kind of nematic ordering. And so the shape of the target zones are anisotropic. And when you then integrate over the anisotropic shape of the target zones, there's one extra power of L that comes into this because the ellipse, the next ellipse that can go into a target zone is typically aligned, so it's got very restricted degrees of freedom. And if you then sort of put that into this line of reasoning and wave your hands a little bit, out will come t to the 1/3. Which I'm not sure I believe, actually. I think that simulations do show something close to that. But the simulations here are extremely difficult to do, and there's still a lot of open questions here. I mean, since you raised the question of ellipses, a very beautiful problem is the problem of absorption of needles, so infinitely thin rods. And there was a paper made about 15 years ago by Taras and Guillot who said that the probability that an absorption event is successful scales as t to the square root of 2 minus 1, so an irrational exponent for the probability of absorption. And if you look at a picture of what the system looks like, it's really nice because there's like little microcrystallites in nematic order and then gaps of all sizes, and there's all kinds of weird twists to the nematic ordering. It's a beautiful problem, and I think it's still not poorly understood. Yeah,
so I'm trying to understand what you wrote down here. So what if you made it, instead of C of L and T, you made it C of A and T, or A is area?
Well, so if I said area, then I just would have put here area.
Okay, area and then...
Yeah.
And then if you wrote that integral below as integral over dl, if you wrote it over dA, would that work or would that be wrong?
Good points. I don't know what to say about that. I haven't thought about that. Kip is always the guy who asks the most difficult questions in my class, so he's only doing it here.
I mean, it seems like you're somehow incorporating a degeneracy.
Yeah. So I think the issue here is that like there's a density of states here. When I change from length to area, I should have density of states factor here. It's not going to change. I mean, I'm going to get the same answer, but how to answer your question off the top of my head, I don't know. But I'm sure I have to put an appropriate density of states factor to make it work.
Yeah, there's some implicit density of states that you assume to be there.
Yes.
Okay, maybe you're going to talk about this later ahead of the game. But suppose that you're now doing. Let's go back to one dimension, and now let's allow these things to diffuse.
Okay.
How does that change the problem?
Excellent question. So let me actually let me tell you what the answer is to that one, because it's a nice little story. It's a sweet story, and it also will be a nice segue to Danny Van Abraham's talk next week. So let's suppose that instead of having perfect absorption, you have imperfect absorption, that once the particles are absorbed, they can diffuse if there's vacancies nearby. Let's talk about just dimer absorption for the sake of simplicity. And let me talk about the extreme limit, where absorption is quick and diffusion is slow. So this separation of timescales is also a very useful device that you can use to simplify the nature of the problem. So if we allow for dimer diffusion, So let's suppose that we wait for t large, so that all absorption events that could have occurred have occurred. And so my line will look something like this. Here is a dimer, and then maybe an empty space. Here's a dimer and a dimer, maybe another dimer and another dimer, another dimer and another dimer, and then here's an empty space, and then dimer, dimer. And so now let's suppose that we allow diffusion to occur. And let's also work in the limit where absorption is so fast that if ever there's a vacancy created that's 2 in a row, then it will be immediately filled up. So for example, if this guy hops, so this guy could hop to the right, or this guy could hop to the left at some slow time scale. Suppose this guy hops to the left, so then I'll have my dimer, and then this guy has moved over here, and now the vacancy has done this. And then I get my 2 dimers here, my 2 dimers here, and this guy over here. And so what you see is that the vacancy is hopped by 2 steps to the right. So in the case of allowing a small amount of dimer diffusion, the vacancies that remain are undergoing diffusion and hopping by a distance 2. And if it so happens that this guy hops and this guy hops, then I'll eventually get to a point that I have these 2 vacancies nearest neighbor, which are then immediately filled. And so this is nothing more than a realization of this 2-body bimolecular annihilation scheme, A plus A going to nothing, for which the density decays as t to the minus 1/2. So minus 1/2. So in this case, once I reach the sort of this large time state where everything that can absorb has absorbed, and I'm reaching this density of 1 minus e to the minus 2, then it approaches 1 with this power law tail to it. Yes?
But you could also solve this by, again, doing the same technology, but adding diffusion as a way of changing your probability, the size.
Absolutely. So, in fact, Danny, I'm sure, is going to give a beautiful lecture on how you use that technology to look at the empty interval evolution because of diffusion, and the problem is eminently soluble, and he'll show you everything.
Is this the regime, if you generalize this to higher dimensions, what would essentially be a random loose packing problem? Because if you allow diffusion, then and if absorption events will eventually occur that can,
right,
then all things will be touching each other,
right,
and you'll end up with some void smaller than the part.
I would have to say I'm not sure how to formulate the problem in greater than 2 dimensions, just for the reason that Biot's mentioned, which is that if I have a cage where a particle could actually fit, but it's blocked by like a spherical region that doesn't have any interstitials that allow it to pass through, then you can't realize it. It could be realized perhaps in 2 dimensions. And in fact, there's been mostly simulational rather than any kind of analytical studies of various sorts of ways of making random loose packings by just dropping particles randomly with maybe slightly different radii so that they won't crystallize, and looking at the area of the packing fractional systems.
What I have in mind is kind of a membrane that has particles absorbing onto it from some sort of gaseous phase around it. So in 2 dimensions is what I think.
Yeah, so I think the problem of sort of parking, like a 2-dimensional parking lot where the particles are spheres, and then there's some jiggling around so they elbow each other away, and then filling in spheres whenever they can. I don't know what to say about that. The analogous problem in 1 dimension, which I guess I'm not going to talk about today because I think I've run out of time and it's a bit too detailed, but we could talk about the analogous problem in 1 dimension. I mean, let me just sort of sketch the issue, because if I imagine now, and for those of you who live in student ghettos, which is probably everybody, you know that all the parking spots in the street are completely parked up and there's like 1 inch of space between the cars. You can ask, so why is that? And the point is that, especially if you have like unrestricted parking spots. So imagine that somebody leaves a parking spot. Well, typically 1 car will fill in. But sometimes you get some global, like cooperative rearrangements where you have like a gap of size 10 inches on a car, and then another car moves and the gap becomes only 1 inch, but then the gap on the other side is 2 feet, and then the next car back, maybe it parks further away, and so this gap gets a little larger by collective rearrangements, until you reach a point where when a car leaves, there's actually 2 spots created. Or for example, when a Lincoln Continental pulls out of a parking spot that 2, politically correct Toyota Priuses can go into it. And so in this process, where one has a small amount of desorption, the system will actually completely fill up along the lines that you are talking about. And in fact, from the experimental perspective, people have done the same kind of experiment with so-called granular compaction, just taking like a column of sand and shaking it and looking at how the density increases. And apparently over time scales of months, shaking it just like this with like a dimensional shaking rate that's sort of the order of gravity or a little bit more than gravity, it seems to be compacting at a rate that goes like, and the log time dynamics is not power law, but 1 over logarithm of the power. So this problem in one dimension has been studied fairly well, and it's in my notes. The two-dimensional analog, I think, is not studied. Kip, you have a question?
Well, I was just going to ask if a particle is a target zone, that could also cover up another target zone, but I guess that's such a second-order effect that we don't care about.
Yeah, so again, in the long-term limit, the target zones will be few and far between, so I wouldn't worry about that.
Does anything interesting happen when you consider surfaces that are flat, but like when you're working on a spherical thing with curvature?
Well, it sounds like a very physical problem, but beyond. I mean, what do you have in mind? Just.
Well, I'm just imagining you have some. Actually, I was thinking of like an equal that has like curvature on the end.
Right.
Working on that.
Well, I think curvature effects, I'm just not sure what to say about them because, I think that effectively one can imagine still treating it as locally flat. But one other thing which maybe is underlying your question is that one asks about things like multi-layer absorption, which is a little bit more more like a higher dimensional element to the problem. And these multi-layer problems are notoriously difficult, and basically there is some work on the subject, but there's not sort of like a clean model or a clean problem that like sort of says here's the right model for multi-layer absorption. But your problem of like absorption, say a finite substrate, say it's a sphere. I think that like suppose I did this, I just had a one-dimensional ring and just absorbed dimers on the ring, then it just seems to me to be nothing more than a finite size analog of the original Flory problem.
But if you had your ring like that and you had like really long.
So you want to have like straight molecules that did something like that?
No, I want to have floppy molecules.
You want to have floppy molecules? Okay, so something that absorbs like that.
Yeah. Maybe it's not very.
Well, I think that there's interesting finite size effects that would go on here, but I think that geometrically this is not really any different than having a flat substrate.
I have a applied question of this parking problem. Like, if you consider the actual parking process, it might be closer to the one of monomer attachment, right? Because you have defined parking spaces and all the cars going into one parking space.
But so you're talking about like a regulated society where like, there's a parking space that's like mapped out with lines and saying one car here and only one car only, and that's it.
But that's pretty much everywhere, right?
No, that might be in like Germanic countries, but certainly not true in student ghettos. I mean in Boston, you have to like park your car in Boston, haven't you? There you'll see that it doesn't. The parking meter is kind of like sort of an advisory capacity.
Okay. But then my question is like, is it possible to if you have like some defined length for this monomer string of parking spaces, and also you have this model of non-defined parking spaces, is it possible to say which parking procedure would accommodate more cars at the end?
But maybe I'm not quite understanding your question, because it seems to me you're saying that there's like monomer-sized parking spaces, and you have monomers which are parking, so that means you'll just completely park up the system.
Yeah, but you have also some length, right, defining your. I'm wondering if for example, so you have a parking lot of some size.
Yeah.
And then you define like a monomer.
So if I understand your problem, here is my parking lot, and here are like the cups that are going to hold my monomers, and the monomer just goes here. So what am I missing in your question?
He wants to compare that to the
to the case where you don't have any pockets.
The continuous case.
Yeah. But the continuous one you always get a higher number.
Well, first of all, in this lattice realization, I'm sort of treating, this empty space here is like not being considered because I'm doing a discrete enumeration, just counting the number of occupied sites divided by the total number of sites. In a continuum, if I imagine putting down cars like this, So again, for this process in one dimension, where I'm just putting them down randomly using unit-sized cars, this will ultimately pack at a density of 0.747 ... without any other relaxation mechanism going on. But here, this corresponds to density equals 1, but density is defined in a discrete sense, and it's just the number of sites occupied divided by the total number of sites, not the area fraction of the substrate. Maybe I'm not quite getting your question.
Yeah, I see your point. Yeah, maybe you need to include some other stuff like parts of different sizes to be able to compare.
Okay, so if you have different sized cars, polydispersed, this is now also a very interesting problem for which there's been an awful lot of work, and I have to admit that I don't know the current state of the art, but say, for example, and this might be even a fun exercise for you, is like study the deposition of dimers and trimers, a mixture of them, and what happens as a function of time. I mean, I think these are all manifestly doable problems, and they might have some interesting results. Well, so somehow it seems that I've taken up all but 3 minutes of the lecture and discussion time, so maybe this is a reasonable place to start.
Yeah, basically.
That's right, but I mean, it seems like I'm taking up the total time for lecture plus discussion. So.
That's fine.
Yeah.
Yeah.
Don't worry about it.
Okay. More questions for this.
Yeah, maybe. Can you make any comment about experiments? You know, so there's a lot of theory, but like, so how much of this is there's some real experiments?
Well, I guess the thing is that there's been a lot of experiments in things like absorbing latex particles and looking at the final rate of absorption is T to the minus 1/2. This asymptotic behavior, I think, is well understood and well characterized experimentally. The thing which I'm a bit more familiar with, and which I didn't have time to talk about, was this assisted polymer translocation, which is that you can, because a lot of these problems involving one-dimensional absorption kinetics, they're naturally applied to polymer systems. And so, the thing of like a polymer translocating through a pore and being assisted by a chaperone, this process, I guess the only thing is that there's not like quantitative measurements, but one sees that the effect of the chaperone assistance is really dramatic, and so the theory that comes from this kind of technology proves that instead of just a polymer diffusing through a pore, it actually moves through at some finite velocity, which is a huge effect. So those sorts of very simple things, is it diffusing or is it drifting, one can see experimentally, but can you actually verify how the velocity depends on the parameters of the system? That's not been done.
And what about sort of from yesterday's lecture, gelation problems? Is that any of that?
Yeah, well, no, the gelation problem has been much better studied experimentally. I mean, I would say that this is sort of like 20 years ago, people were doing neutron scattering experiments to look at the cluster size distribution and verifying many elements of the classical gelation theory. So that is pretty well understood, and it's kind of amazing that mean field theory works as well as it does. Yeah, it works.
So that we always talk about cars and so on. Did anybody ever study one of the car parking in Boston or wherever?
Yeah, actually, there was a paper on the archive maybe about 5 years ago where some guys just went along like some streets. I don't know if they did it in New York or maybe Zurich or something. What?
Einstein.
He did that?
Einstein?
No, not that Einstein. Einstein. But anyways, they walked along the streets and just measured the distance between every single parked car, and then used that to measure the distance distribution between parked cars and compare it with the theory that I didn't present today. But it says that it should be an exponential distribution, and more or less it worked. Yeah. So it's actually some of these dorky things that you just look around you and the parked cars and what's going on there. It fits with it's a nice non-equilibrium standard problem.
You can get the grant from DOT.
Yeah, no, they don't have any money. No talent. Yes.
Sorry, so in real life, though, the car parking problem is going to be more of an absorption-desorption problem, right?
Right.
Because people are going to want to leave eventually.
Correct.
So does the asymptotic limits, like the steady state, does that...
Well, so again, it's in the notes that you have, but I didn't have time to speak about it, but when you have desorption as well as adsorption, the problem is actually really interesting, because in the case of irreversible car absorption, this rho final, this rho infinity, is equal to 0.747 ... And of course, since we all, at some point in our lives we've all lived in student ghettos, we know that the density of cars parked is not 3/4 of the space, but it's almost 1. And the point is that if you allow a very small amount of desorption, the density actually goes asymptotically to 1. And the only thing which prevents it in a city like Boston is that some people at least believe in parking meters, and there's also intersections and things like that, so you don't have an infinite line, you just have a finite line.
People have discussed absorption and then some kind of interaction between things that are absorbed, so they might be sort of a monomer coming down might be more likely to absorb closer to other monomers.
Okay. Well, let me tell you one case that can be solved by this technology, which is the following. Let's imagine you have monomer absorption, only monomer absorption, but if a monomer is here, and then here's the next absorption site, but the probability that a monomer absorbs near its neighbor is different. So if it absorbs like out here in the wilderness, it absorbs with rate 1. So this is rate 1. And here, you can say it absorbs with rate R. And R could be either bigger than 1, so it's like it's attracting, or it could be less than 1, which is repelling. Using the same empty integral technology, you can solve this problem as well. And it's been done. Again, there's all kinds of I highly recommend this review article by Jim Evans from the Reviews of Modern Physics, and you'll find like all this. It goes under the terminology cooperative monomer absorption or cooperative absorption. So a lot has been done, but I don't know if everything has been done. Again, I have never worked in this field of absorption kinetics, so I'm only a novice and know literature. But I highly recommend Jim Evans' review article.
Are there some studies that look up, for example, dimers and monomers and many of these kinds together?
Yeah,
like for example, here in the lecture hall, so that people come along and some of them in pairs or in couples. And
yeah, well, so that's an exercise you can do. Is like we can study the problem of monomers and dimers absorbing on a one-dimensional line. What's the final coverage? I mean, these problems have been studied, but that one in particular is simple enough that you could probably solve it just based on what you heard in today's lecture. So exercise for the students.
But in any process with monomers, the final coverage has to be 1, right?
Yes. But the interesting thing is that suppose that the rate of monomer absorption and dimer absorption is different. Mm-hmm. And then, so in some sense, like suppose that dimer absorption is very quick. Then you'll end up with this 0.866 coverage, and then the rest will fill in very simply. So yeah, maybe monomer-dimer isn't so interesting, but dimer-trimer is still interesting. So you need to have, monomers sort of like heal all wounds in some sense, so it's going to be perfect again.
All right. Perfect timing. Thanks very much.